Hi everybody, welcome back to Climate Change Calculated, today number 9 about durability and convenience of electric vehicles. My name is Gerald Schuller and this is my little climate change assistant who can now also speak. Okay, so let me start with my new channel chatbot. So we have a new channel chatbot which I call Climate Change Assistant. And here you can see the link, and you can also take this QR code, scan it with your smartphone, and then you should be on the same page. So I made this new specialized channel chatbot, whom I gave this context of this channel. And hence it gives a more targeted and precise answer than general chatbots. And it can also answer basic questions and also more advanced ones and specialized ones to your personal background, or in which episode a topic was treated. It is based on OpenAI's ChatGPT. But of course, asking questions in the comments is also possible. And while you're at it, you can also leave a like for me. Okay, so let's start with today's topic. The transportation sector significantly contributes to global CO2 emissions. So particularly here in this case for the EU, you can see here the transport sector has 28.5% of the CO2 share, and of it the road transport is 20.5%, and aviation is altogether about 4%. And aviation flying is really difficult to electrify. But road transport is actually quite easy, as we will see. Electric cars, electric buses, electric trucks is all already there and feasible. So it's kind of a low-hanging fruit. It's available, it's practical, it just needs to be used and bought. So what can we do? Well, what we can do is create demand for renewable energy technologies to stimulate the economic and political process of energy transition, because only with these technologies we can achieve the necessary CO2 reductions of at least 80%. And this number I showed in my first episode, Climate Change Calculated number 1. And this reduction number was necessary to only to not further increase the CO2 concentration in our atmosphere. But in practice, we want to reduce it, so we actually have to reduce even more than this 80%. And those who buy new cars or trucks or buses determine the composition of the nation's vehicle fleet of that year. So they create demand, and also those cars, they will last for a while, as we will see, and have a lasting impact. And also, we are in a kind of an S-curve of technology adoption, and the more demand there is, the more will be produced, and the more economically the production will be, and the prices will fall, and then the adoption will further increase. So that's basically keeping that cycle rolling. Okay, so electric cars or electric vehicles are an important building block in the transition to renewable energies, because they do not require any fossil fuels. So if we have electricity, we can run it, and the electricity can come from renewable energy. And also, plus, they are 3 times more energy efficient than combustion engines, and therefore correspondingly cheaper to operate. So combustion engines, physics tells us there's a limit on energy efficiency, and that makes them very inefficient, particularly those small combustion engine in cars. They have an efficiency of often less than 30%, whereas electric cars, they come around 90%. So that's much better. And they are already practical and convenient, as I will show. So my personal EV experiences, I have a Tesla Model S from 2018, And I drive it already for over 200,000 kilometers. So it's like now 7 years and 200,000 kilometers. So I have some experience. So at that time, 2018, it was probably the only practical long-range electrical car in Germany. The Model 3 did not arrive in Germany until a year later. And Tesla was and remains a global leader in technology and sales. But Chinese manufacturers are catching up quickly. So hopefully this diversity will lead to a faster increase in the share of electric cars in sales. So hopefully competition will increase the share. Although that was already said in 2018. So we have to see. It's quite a lot of dynamic. So my experiences in this time, since I have this car, since 2018, I didn't notice any battery degradation. So it's still like in the beginning, almost like new. And also, very convenient, hardly any maintenance is required. No inspections, no oil change, no water change. It's really convenient. Also, no noticeable range reduction from heating or air conditioning. So if I turn on my air conditioning in summertime or heating in the wintertime, I don't notice any range reduction. In wintertime in general, it has less range because of the road conditions and the cold, but that's only about like 10-20%. So it's okay. It's noticeable, but not dramatic. Also, I find it's very convenient and practical for charging, as we'll see. And with all its active and passive safety systems, I found it is probably the safest car on the road. For instance, it brakes before I can react. It has a steering correction to avoid collisions, and it ignores accidental wrong input from me, like engagement of the parking gear on the highway. So it's really, it saved a few times my life, kind of. So here's a link for it, the Tesla Impact Report. And for the batteries, often I found people asking, yeah, how long will those batteries last? Maybe as long as my cell phone? Well, actually I found a nice dissertation from TU Munich about aging of 18650 battery cells. So these are the cells which are used by Tesla Model S, for instance, or also power tools. So these are different kinds of batteries, different from cell phones. So they are more big. They are kind of like cylindrical cells, and they are more powerful than those small cell phone cells. And this dissertation shows that after 2000 full cycles, 80% capacity remains. So this sounds a little bit abstract. 2000 cells, full cycles, yeah, okay. 80%, yeah, it's basically almost like new. But then one full cycle means a full range for the car. So one cycle, so roughly 500 kilometers. And if you multiply those 2000 by the 500 kilometers, you get to a 1 million kilometer lifespan. So that's quite a lot, right? So there's actually little variance on this number, so this sounds like a fixed number, but it's actually it's a certain variance, but it's still quite a good number. So this data suggests that many packs outlive the rest of the car, and then you have second life storage markets that extend the usefulness further, for instance for stationary storage. Yeah, so here is the dissertation. You can see in the literature. Yeah, and this dissertation also has a prediction about the calendar life of the batteries. So it says 90% capacity remains after 20 years if we keep it at a medium charge level, like in between 10 and 90% of charge. And that's also quite a lot. So even after 20 years, if you treat the battery decently, don't let it really run empty for a long time or keep it charged at 100% for a long time, it will still be as good as new after 20 years. So that's quite nice. Yeah, so maybe now we can try our channel chatbot. the climate change assistant. And we can ask it, maybe also to get an idea about the variance, the standard deviation of how long does the Tesla battery last. So as we'll see, it gives actually quite a nice idea. So we can try. So you can also try it at home. So let me copy this question here. And then we can go to our chatbot. So this gets me to my chatbot. It starts it. So here we can see it. And maybe first I ask it to introduce itself. So please introduce yourself. So let's see what it says. It's always an interesting experiment because every time the answer is slightly different. Yeah, so it's kind of nice. So maybe I can make the font a little bit bigger. Yeah, hi there. I'm your climate change assistant, your friendly guide through the science, data and solutions behind climate change, especially as presented in the YouTube channels Climate Change Calculated in English and Klimawandel nachgerechnet in German by Professor Gerald Schuller. That's me from TU Ilmenau. So I'm a media technology professor who uses math, physics, Python and open data to check climate change claims with clear, reproducible calculations. The goal is nachrechnen statt nachreden. Do the math instead of just repeating stories. Yeah, so it's actually quite nice. So with me you can dive deeper into episodes, understand concepts like radiative forcing, CO2 emissions, e-mobility and more. Get help creating bilingual episode scripts or slides. Explore open data for your own climate change calculations. We mix solid science with a pinch of curiosity and a dash of wit, always in English and German, unless you prefer otherwise. So it's a multilingual assistant, so you can also use your own language if you like. So now we can ask it about the battery. So let's try. How long does the Tesla drive battery last? Let's try. See what it does. Great question. Tesla's drive batteries are designed for long-term durability, and we've got solid data on this from both real-world experience and scientific studies. Key points: design life. Tesla's lithium-ion cells, like the 18650 or 2170 types, are engineered for about 2000 full charging cycles, like in the study. One cycle is charging from 0% to 100% once. In practice, partial cycles, e.g. 30% to 80%, count fractionally. Yeah, that's actually a good point, right? In practice, you wouldn't go from 0 to 100 or from 100 to 0, but maybe between 30 and 80. But then it just counts accordingly, fractionally. Yeah, so here my practical example. I have driven my Tesla for 200,000 kilometers over 6 years, almost 7 now, and I report no noticeable battery degradation. Yeah, and then here's the study from TU Munich, right, which I just showed. And at medium charging levels, keeping charge between 10 and 90%, batteries can last up to 30 years with a state of health of 90%. Yeah, this is also what we just saw. And range perspective, if you drive about 15,000 to 20,000 kilometers per year, a 2000 cycle battery easily covers 400,000 to 500,000 kilometers or 20 to 25 years of use. So this one is actually a little bit more conservative estimation, as I just did with this 1 million kilometer. But this also shows kind of the range that we can expect. So it's something like 400, 500,000 up to 1 million kilometers. So bottom line, Tesla drive batteries are robust, designed for decades and capable of lasting several 100,000 kilometers with proper care. The main tips: avoid frequent full charges, keep battery levels moderate, and don't let it drop to 0%. Well, that's a good tip. Okay, so then we can go back to the slides. So that was quite a nice answer. Yeah, then there's also the mechanical durability. And in internal combustion engine cars, the most moving parts are in the engine. In electric cars, actually the engine doesn't have much moving parts. So that's one of the big advantages. And also it has no high pressures or high temperatures, which means we have less wear and tear. And that leads to the lower maintenance costs and hence the longer service life than the internal combustion engine vehicles. And I also found this link here to the Wired magazine titled "Electric Cars Could Last Much Longer Than Most Think." Yeah, that's the point here. So Wired found EV lasts 20 plus years. Yeah. And for ICE cars, it's 15 years on average. I also found this nice link here, EV Clinic. They specialized on EV repairs, and they have some on their website some hints what to check. I found that quite practical. Yeah, then the question is the future resale value. I found many people are not quite sure how the value of their car, of their EV, might depreciate over the time. And that's because the used car market still lacks long-term experience with electric cars. But it could settle at the following levels, where I used the numbers that we just saw now. So the economic service life of a car is the service life of the most expensive unit. That's either the combustion engine in the ICE car or the battery in an EV. So the combustion engine car has an average service life of about 15 years, as we just saw. So then the question is, how long does the electric car life, how long does it last? And we saw, just assuming we have about 1 million kilometers and an average of 15,000 kilometers per year, the service life would be 66 years. So that's kind of the optimistic side here. If we have just 500,000 kilometers, we would be at the 30 years that we just saw. But it's still quite substantially longer than for internal combustion engine cars. So this is a theoretical number, but an entirely possible value. So let's assume we have those two numbers, and then we can compare how the value might depreciate over time. So for that, I plotted this number. So I assumed the new value of the car of 40,000 euros and residual value at the end of life of 1,000 euros. So this is a junk value. So with a typical exponential decline in value, we get this curve, which we see here for the resale value. And this shows that the loss in value of the electric car over time should slow down significantly. So here you can see the end of life. The red curve is the internal combustion engine car. So after 15 years, it reaches this 1,000 euro remaining value. And the green curve is for the electric car. Here we have the 66 years, where it reached the 1,000 euro remaining value. And both start at 40,000 euros. And then we can see here, when we look when it reaches half value, 20,000, then the internal combustion engine here, this is about 3 years. And I found this is actually a realistic value. After 3 years, most conventional cars lose half their value. But then if you predict using this longer service life of the electric car, then for 20,000 euros value, we would already be here at about 12 years. So it's about 4 times as long. So that means the depreciation is about 4 times as slow as for an internal combustion engine. So that probably means in maybe 30 years we have many more EV old-timers than combustion engine old-timers or historic cars. Yeah, so that's good. That means the value loss from depreciation is much lower, will be much lower in the future than it is now. So next is the charging convenience. So many people ask me, yeah, but where can I charge my car? Actually, home or work charging is quite simple and clean. You can simply use your normal 230 volt outlet. It doesn't need to be any specific or special outlet. And you can just plug your car in overnight. And even if you don't use the car for a long time, you can still leave it plugged in and set it to like 80%, 80 or 90% of the state of charge. Usually you can enter it in the car, you can set the maximum level, and then it can sit there for a long time. So overnight you can charge 150 to 200 kilometers usually, and that's usually more than enough for the daily commute. Yeah, and again we can use our chatbot to ask, for instance, my electric Tesla consumes about 16 kilowatt hours per 100 kilometers. So this is kind of like a characteristic value that you should watch for in your car. 16 kilowatt hours per 100 kilometers is actually quite a good value, particularly for such a big car. And that's because Tesla, they are in general very energy efficient, so often more energy efficient than other electric cars, and that's also why they have a good range and low maintenance cost. So this is the important number here, 16 kilowatt hours per 100 kilometers. This is the consumption. If I plug it into my power outlet at 7 p.m. and drive off again at 8 a.m. in the morning, how many kilometers will it have recharged in that time? So again, that answer gives a good idea. So this also shows you how you can do it yourself using your own numbers. So we can go back to our climate change assistant. I copy that question here and paste it into our climate change assistant and ask it. Let's see what it says. Yeah, great. Let's break this down with a bit of delightful math. Yes, great. Your inputs, consumption, 16 kilowatt hours per 100 kilometers. Yeah, the key number here. Charging time from 7 p.m. to 8 a.m., which is 13 hours. Charging at a standard home outlet, which typically delivers about 2.3 to 3 kilowatt of power. So this is the typical number. So if you didn't know, the climate change assistant knows, depending on voltage and ampere. So it depends a little bit of what kind of outlet you have. So we'll use 3 kilowatt as Professor Schuller does in his Tesla example. Yeah. So here it actually explains the computation, which is kind of nice. Energy is power times time. So here we have 3 kilowatt times 13 hours. So we get 39 kilowatt hours. So the range per kilowatt hour. So we have 1 kilowatt hour is 100 kilometers divided by 16. So we have 6.25 kilometers per kilowatt hour. And total range recharged, 13 kilowatt hours times 6.25. This is this number here. So we have 2 kilowatt hours times kilometers divided by kilowatt hours. So the kilowatt hours cancel, the kilometers remain. So this is kind of a cross check, and we get 240 kilometers. So this is actually quite a good value. So it's even a little bit more than the 200 kilometer I just mentioned. So if you plug your Tesla in at 7 p.m. and charge at 3 kilowatt until 8 a.m., you'll have reached about 244 kilometers of range by the next morning. Yeah. Let me know if you'd like to adjust for a lower power outlet, for instance 2.3 kilowatt, or charging losses 10%. Yeah. Depends, yeah, but 10% seems to be kind of realistic. So it actually takes into account even those little effects here, less power and some charging losses, and gives you the typical numbers for those power outlets. So I think it's actually quite a nice help. Yeah, so let's continue here. Yeah, so if you don't charge at home, I often also have people asking me, yeah, what if I cannot charge at home? Well, there are many public fast chargers around. And for instance, you can find many at shopping malls or near restaurants. So this picture shows actually a charger next to a restaurant. So this is also what I'm doing when I'm traveling. I usually, when I go shopping or when I go for eating, I look for a place which has a supercharger or a fast charger, and this is where I can then charge while I'm shopping or eating. And even if I don't charge in full, it's still good enough for the rest of the week. Yeah, and in general, this also is a low cost. So this 40 cent per kilowatt hours is like the domestic rate for electricity. So if you use this 16 kilowatt hour per 100 kilometers, then this comes to about 6.4 euros per 100 kilometers. Which in Germany is about 1/3 or 1/2 of the comparable gasoline cost for comparable cars. So it's actually quite a lot of savings. Superchargers might have higher prices, depends on where they are. Yeah, and I also found this link here, this report on it. Yeah, and I mentioned the charging infrastructure is actually quite good. There are more charging stations than gas stations in Germany. With fast chargers, about 100 kilowatts, which is actually not very fast, you can add 300 kilometers in 30 minutes. So the newest chargers have like 300, 250, 350 kilowatts. They're actually much more powerful. Yeah, but even with those, you get a decent range addition in half an hour when you do your eating, for instance, or getting a coffee. Yeah, and superchargers are about every 10 to 50 kilometers on highways, and the numbers are always increasing. But fast chargers are less conspicuous than gas stations. So they're not as obvious. Gas stations, they have big signs and they are obvious, but chargers are small and usually behind buildings. But for that, they are listed in the car's navigation system or in Google Maps. So electronically, they are easily to find. The car navigation system has an integrated supercharger occupancy display, allowing it to automatically navigate to the most convenient ones. So that's particularly the case for Tesla. When you navigate to a destination, it automatically plans the route, including possible supercharger stops at the most convenient ones. And if it finds on the way that one is getting too crowded, then it automatically routes you to the next one, for instance, or an earlier one, depending on what's more convenient. Also, Tesla has a nice invention. It has this automatic charging authentication. Already since about 2012, they had this idea. So for charging, you simply plug in and the car takes care of automatic authentication. So you don't need to do it manually using your smartphone or cards to authenticate. The car does it for you. It's very convenient. So you just plug in and off you go and it charges. And other car manufacturers are working on it, on the standard plug and charge, which basically has the same functionality. So they're also now getting to it. They just took longer. Yeah, here you can see some of the sources. Yeah, so altogether I found electric cars have a much better user experience than internal combustion engine cars. And this is also why people who start with electric cars usually don't switch back. Driving an electric car is relaxing and also fun. It is silent and smooth driving. And at the same time, you have this instant torque, which makes it very powerful. And also you have much lower running costs for the car. So the maintenance is much lower. Yeah, what I found interesting is recently the new Tesla Impact report came out. I find them interesting because they have many internal statistics, internal from the industry. So it's sometimes quite interesting. Yeah, and also it's nice to read. So here I found on page 12, it states the CO2 savings of a car over time. The CO2 emissions caused by manufacturing are offset after only about 3.5 years of the car's lifetime compared to an internal combustion engine car. So this is also what I hear sometimes, this CO2 overhead caused by manufacturing of the battery. But it's actually quite short to recover it. And also I found in Germany it could be even less, because the Gigafactory at Berlin-Brandenburg has been powered by 100% renewable electricity for 2 years now. So basically they have no CO2 overhead from manufacturing the cars, maybe from imported cars. So that could be even less than the 3.5 years. Yeah, so after that, the remaining lifetime, the remaining 60 years maybe, it's all positive. Right, so it's over the lifetime of the car, it's a big difference. Yeah, here are further example chatbot questions. That's for you to try on your own. Like, how many people die per year in the city like Berlin from the consequences of air pollutions and the effects of climate change? And then, how many lives can my electric Tesla save per year compared to a car with an internal combustion engine? Yes, those are very fundamental and maybe a little bit witty questions. So yeah, go ahead and try them out. Yeah, this leads me to my conclusion. Don't be discouraged by media or politics. EVs offer better experience, lower cost, higher durability. They're a sustainable and economical transport solution. And again, here's a link to my new climate change calculated YouTube channel chatbot. Try it out. Yeah, and here are my references, which should be also in the description. Okay, so that's it for today. Then, yeah, have a nice time and see you next time. Bye bye.